Chapter 9. Getting the Range. Every person with a good pair of eyes in his head is a range finder. He may not know it, but he is, just the same, and the way to prove it is to try a little range finding on a small scale. Use the top of a table for your field of operations and pick out some spot within easy reach of your hand for the target whose range you wish to find. The target may be a penny or a small circle drawn on a piece of white paper. Take a pencil in your hand and imagine it as a shell which you are going to land on the target. It is not quite fair to have a bird's eye view of the field, so get down on your knees and bring your eyes within a few inches of the top of the table. Now close one eye and, making your hand describe an arc through the air like the arc that a shell would describe, see how nearly you can bring the pencil point down on the center of the target. Do it slowly, so that your eye may guide the hand throughout its course. You will be surprised to find out how far you come short or overreach the mark. You will have actually to grope for the target. If by any chance you should score a hit on the first try, you may be sure that it is an accident. Have a friend move the target around to a different position and try again. Evidently, with one eye you are not a good range finder. But now use two eyes and you will score a hit every time. Not only can you land the pencil on the penny, but you will be able to bring it down on the very center of the target. The explanation of this is that when you bring your eyes to bear upon any object that is nearby, they have to be turned in slightly so that both of them shall be aimed directly at that object. The nearer the object, the more they are turned in, and the farther the object, the more nearly parallel are the eyes. Long experience has taught you to gauge the distance of an object by the feel of the eyes, that is, by the effort your muscles have to make to pull the eyes to a focus, and in this way the eyes give you the range of an object. You do not know what the distance is in feet or inches, but you can tell when the pencil point is moved out until it is in the same focus as the target. The experiment can be tried on a larger scale with the end of a fishing rod, but here you will probably have to use a larger target. However, there is a limit to which you can gauge the range. At a distance of, say, 15 or 20 feet, a variation of a few inches beyond or this side of the target makes scarcely any change in the focus of the eyes. That is because the eyes are so close together. If they were farther apart, they could tell the range at much greater distances. Spreading the eyes far apart. Now, the ordinary range finder used in the Army and in the Navy is an arrangement for spreading the eyes apart to a considerable distance. Of course, the eyes are not actually spread, but their vision is. The range finder is really a double telescope. The barrel is not pointed at an object, but it is held at right angles to it. You look into the instrument at the middle of the barrel and out of it at the two ends. A system of mirrors or prisms makes this possible. The range finder may be a yard or more in length, which is equivalent to spreading your eyes a yard or more apart. Now, the prisms or object glasses at the ends of the tubes are adjustable so that they will turn in until they focus directly on the target whose range you wish to find, and the angle through which these glasses are turned gives a measure of the distance of the target. The whole thing is calculated out so that the distance in feet, yards, or meters, or whatever the measure may be, is registered on a scale in the range finder. Ordinarily, only one eye is used to look through the range finder, because the system of mirrors is set to divide the sight of that one eye and make it serve the purposes of two. That leaves the other eye free to read the scale, which comes automatically into view as the range finder is adjusted for the different ranges. On the battleships, enormous range finders are used. Some of them are 20 feet long. With the eyes spread as far apart as that, and with a microscope to read the scale, you can imagine how accurately the range can be found, even when the target is miles away. But on land such big range finders cannot conveniently be used, they are too bulky. When it is necessary to get the range of a very distant object, two observers are used who are stationed several hundred yards apart. These observers have telescopes which they bear upon the object, and the angle through which they have to turn the telescope is reported by telephone to the battery, where, by a rapid calculation, it is possible to estimate the exact position of the target. Then the gun is moved up or down, to the right or to the left, according to the calculation. The observers have to creep as near to the enemy as possible, and they must be up high enough to command a good view of the target. Sometimes they are placed on top of telegraph poles, or hidden up a tall tree, or in a church steeple. Getting the observer off the ground. This was the method of getting the range in previous wars, and it was used to a considerable extent in the war we have just been through. But the great European conflict brought out wonderful improvements in all branches of fighting, and range finding was absolutely revolutionized, because shelling was done at greater ranges than ever before, but chiefly because the war was carried up into the sky. A bird's eye observation is much more accurate than any that can be obtained from the ground. Even before this war, some observations were taken by sending a man up in a kite, particularly a kite towed from a ship, and even as far back as the Civil War, captive balloons were used to raise an observer to a good height above the ground. They were the ordinary round balloons, but the observation balloon of today is a very different looking object. It is a sausage-shaped gas bag that is held on a slant to the wind like a kite, so that the wind helps to hold it up. To keep it head on to the wind, there is a big air bag that curls around the lower end of the sausage. This acts like a rudder and steadies the balloon. Some balloons have a tail consisting of a series of cone-shaped cups strung on a cable. A kite balloon will ride steadily in a wind that would dash a common round balloon in all directions. Observers in these kite balloons are provided with telephone instruments by which they can communicate instantly with the battery whose fire they are directing. But a kite balloon is a helpless object. It cannot fight the enemy. The hydrogen gas that holds it up will burn furiously if set on fire. In the war, an enemy airplane had merely to drop a bomb upon it or fire an incendiary bullet into it, and the balloon would go up in smoke. Nothing could save it once it took fire, and all the observers could do was to jump for their lives as soon as they saw the enemy close by. They always had parachutes strapped to them, so they could leap without an instant's delay in case of sudden danger. At the very first approach of an enemy airplane, the kite balloon had to be hauled down or it would surely be destroyed, and so kite balloons were not very dependable observation stations for the side which did not control the air. As stated in the preceding chapter, just before the fighting came to an end, our Army was preparing to use balloons that were not afraid of flaming bullets because they were filled with a gas that would not burn. Making maps with a camera. Because airplanes filled the sky with eyes, everything that the Army did near the front had to be carefully hidden from the winged scouts. Batteries were concealed in the woods or under canopies where the woods were shot to pieces, or they were placed in dugouts so that they could not be located. Such targets could seldom be found with a kite balloon. It was the task of airplane observers to search out these hidden batteries. The eye alone was not depended upon to find them. Large cameras were used with telescopic lenses which would bring the surface of the earth near while the airplane flew at a safe height. These were often motion picture cameras which would automatically make an exposure every second or every few seconds. When the machine returned from a photographing expedition, the films were developed and printed, and then pieced together to form a photographic map. The map was scrutinized very carefully for any evidence of a hidden battery or for any suspicious enemy object. As the enemy was always careful to disguise its work, The camera had to be fitted with color screens which would enable it to pick out details that would not be evident to the eye. As new photographic maps were made from day to day, they were carefully compared one with the other, so that it might be seen if there was the slightest change in them which would indicate some enemy activity. As soon as a suspicious spot was discovered, its position was noted on a large-scale military map, and the guns were trained upon it. Correcting the aim. It is one thing to know where the target is, and another to get the shell to drop upon it. In the firing of a shell a distance of 10 or 20 miles, the slightest variation in the gun will make a difference of many yards in the point where the shell lands. Not only that, but the direction of the wind and the density of the air have a part to play in the journey of the shell. If the shell traveled through a vacuum, it would be a much simpler matter to score a hit by the map alone. But even then there would be some differences, because a gun has to be warmed up before it will fire according to calculation. That is why it is necessary to have observers, or spotters as they are called, to see where the shell actually do land and tell the gun pointers whether to elevate or depress the gun, and how much to traverse it, that is, move it sideways. This would not be a very difficult matter if there were only one gun firing, but when a large number of guns are being used, as was almost invariably the case in the war, the spotter had to know which shell belonged to the gun he was directing. One of the most important inventions of the war was the wireless telephone, which airplanes used, and which were brought to such perfection that the pilot of an airplane could talk to a station on the earth without any difficulty from a distance of 10 miles, and in some cases he could reach a range of 50 miles. With the wireless telephone, the observer could communicate instantly with a gun pointer and tell him when to fire. Usually 30 seconds were allowed after the signal sent by the observer before the gun was fired, and on the instant of firing a signal was sent to the man in the airplane to be on the lookout for the shell. Knowing the position of the target, the gun pointer would know how long it would take the shell to travel through the air, and he would keep the man in the airplane posted, warning him at 10 seconds, 5 seconds, and so forth, before the shell was due to land. In order to keep the eyes fresh for observation and not to have them distracted by other sights, the observer usually gazed into space until just before the instant the shell was to land. Then he would look for the column of smoke produced by the explosion of the shell, and report back to the battery how far wide of the mark the shell had landed. A number of shell would be fired at regular intervals, say 4 or 5 per minute, so that the observer would know which shell belonged to the gun in question. There are different kinds of shell. Some will explode on the instant of contact with the earth. These are meant to spread destruction over the surface. There are other shell which will explode a little more slowly, and these penetrate the ground to some extent before going off. While a third type has a delayed action and is intended to be buried deep in the ground before exploding, so as to destroy dugouts and underground positions. The bursts of smoke from the delayed action shell and the semi-delayed action shell rise in a slender vertical column and are not so easily seen from the sky. The instantaneous shell, however, produces a broad burst of smoke which can be spotted much more readily, and this enables the man in the airplane to determine the position of the shell with greater accuracy. For this reason, instantaneous shell were usually used for spotting purposes, and after the gun had found its target, other shell were used suited to the character of the work that was to be done. Miniature battlefields. Observation of shell fire from an airplane called for a great deal of experience, and our spotters were given training on a miniature scale before they undertook to do spotting from the air. A scaffolding was erected in the training quarters over a large picture of a typical bit of enemy territory. Men were posted at the top of this scaffolding so that they could get a bird's eye view of the territory represented on the map, and they were connected by telephone or telegraph with men below who represented the batteries. The instructor would flash a little electric light here and there on the miniature battlefield, and the observers had to locate these flashes and tell instantly how far they were from certain targets. This taught them to be keen and quick and to judge distance accurately. Airplane observing was difficult and dangerous and often impossible. On cloudy days the observer might be unable to fly at a safe height without being lost in the clouds. Then dependence had to be placed upon observers stationed at vantage points near the enemy or in kite balloons. Spotting by sound. When there is no way of seeing the work of a gun, it is still possible to correct the aim because the shell can be made to do its own spotting. Every time a shell lands, it immediately announces the fact with a loud report. That report is really a message which the shell sends out in all directions with a speed of nearly 800 miles per hour, 1,142 feet per second, to be exact. This sound message is picked up by a recorder at several different receiving stations. Of course, it reaches the nearest station a fraction of a second before it arrives at the next nearest one. The distance of each station from the target is known by careful measurement on the map, and the time it takes for sound to travel from a target to each station is accurately worked out. If the sound arrives at each station on scheduled time, the shell has scored a hit, but if it reaches one station a trifle ahead of time and lags behind at another, that is evidence that the shell has missed the target, and a careful measure of the distance in time shows how far and in what direction it is wide of the mark. In this way it was possible to come within 50 or even 25 yards of the target. This sound method was also used to locate an enemy battery. It was often well nigh impossible to locate a battery in any other way. With the use of smokeless powder, there is nothing to betray the position of the gun except the flash at the instant of discharge, and even the flash was hidden by screens from the view of an airplane. Aside from this, when an airplane came near enough actually to see one of these guns, the guns would stop firing until the airplane had been driven off. But a big gun has a big voice, and it is impossible to silence it. Often a gun whose position has remained a secret for a long time was discovered because the gun itself peached. The main trouble with sound spotting was that there were usually so many shell and guns going off at the same time that it was difficult, if not impossible, to distinguish one from another. Sometimes the voice of a hidden gun was purposely drowned by the noise of a lot of other guns. After all, the main responsibility for good shooting had to fall on observers who could actually see the target, and when we think of the splendid work of our soldiers in the war, we must not forget to give full credit to the tireless men whose duty it was to watch, to the men on wings who dared the fierce battle planes of the enemy, to the men afloat high in the sky who must leap at a moment's notice from under a blazing mass of hydrogen, and finally to the men who crept out to perilous vantage points at risk of instant death in order to make the fire of their batteries tell. End of chapter 9. Chapter 10. Talking in the Sky. In one field of war invention, the United States held almost a monopoly, and the progress Americans achieved was epoch-making. Before the war, an aviator, when on the wing, was both deaf and dumb. He could communicate with other airplanes or with the ground only by signal, or, for short distances, by radiotelegraphy, but he could not even carry on conversation with a fellow passenger in the machine without a speaking tube fitted to mouth and ears so as to cut out the terrific roar of his own engine. Now the range of his voice has been so extended that he can chat with fellow aviators miles away. This remarkable achievement, and many others in the field of radio communication, hinge upon a delicate electrical device invented by de Forest in 1906, and known as the audion. For years this instrument was used by radiotelegraphers without a real appreciation of its marvelous possibilities, and, as a matter of fact, in its earlier crude form, it was not capable of performing the wonders it has achieved since it was taken over and developed by the engineers of the Bell telephone system. The audion. Although the audion is familiar to all amateur radio operators, we shall have to give a brief outline of its construction and operation for the benefit of those who have not had the opportunity to dabble in wireless telegraphy. The audion is a small glass bulb from which the air is exhausted to a high degree of vacuum. The bulb contains three elements. One is a tiny filament which is heated to incandescence by a battery, so that it emits negatively charged electrons. The filament is at one side of the bulb, and at the opposite side there is a metal plate. When the plate and the filament are connected with opposite poles of a battery, there is a flow of current between them, but because only negative electrons are emitted by the filament, the current will flow only in one direction, that is, from the plate to the filament. If the audion be placed in the circuit of an alternating current generator, it will let through only the current running in one direction. Thus it will rectify the current, or convert alternating current into direct current. But the most important part of the audion, the part for which de Forest is responsible, is the third element, which is a grid or flat coil of platinum wire placed between the filament and the plate. This grid furnishes a very delicate control of the strength of the electric current between plate and filament. The slightest change in electric power in the grid will produce large changes of power in the current flowing through the audion. This makes it possible to magnify or amplify very feeble electric waves, and the extent to which the amplifying can be carried is virtually limitless, because a series of audions can be used, the current passing through the first being connected with the grid of the next, and so on. Talking from New York to San Francisco. There is a limit to which telephone conversations can be carried on over a wire, unless there is some way of adding fresh energy along the line. For years all sorts of experiments were tried with mechanical devices which would receive a telephone message and send it on with a fresh relay of current. But these devices distorted the message so that it was unintelligible. The range of wire telephony was greatly increased by the use of certain coils invented by Pupin, which were placed in the line at intervals. But still there was a limit to which conversation could be carried on by wire, and it looked as if it would never be possible to telephone from one end of this big country of ours to the other. But the audion supplied a wonderfully efficient relay, and one day we awoke to hear San Francisco calling "Hello" to New York. Used as a relay, the improved audion made it possible to pick up very faint wireless telegraph messages, and in that way increased the range of radio outfits. Messages could be received from great distances without any extensive or elaborate aerials, and the audion could be used at the sending station to magnify the signals transmitted and send them forth with far greater power. Having improved the audion and used it successfully for long-distance telephone conversation over wires, the telephone company began to experiment with wireless telephony. They believed that it might be possible to use radio telephony in places where wires could not be laid. For instance, it might be possible to talk across the Atlantic. But before we go farther, just a word of explanation concerning radiotelegraphy and radiotelephony, for the benefit of those who have not even an elementary knowledge of the subject. Simple explanation of radiotelegraphy. Suppose we should set up two stakes in a pond of water at some distance from each other, and around each we set a ring-shaped cork float. If we could move one of those floats up and down on its stake, it would produce ripples in the water, which would spread out in all directions and finally would reach the opposite stake and cause the float there to bob up and down in exactly the same way as did the float moved by hand. In wireless telegraphy, the two stakes are represented by antennae or aerials, and the cork floats are electric charges, which are sent oscillating up and down the antenna. The oscillations produced at one aerial will set up electromagnetic waves, which will spread out in all directions in the ether until they reach a receiving aerial, and there they will produce electric oscillations similar to the ones in the transmitting antenna. Telegraph signals are sent by the breaking up of the oscillations at the transmitting station into long and short trains of oscillations corresponding to the dots and dashes of ordinary wire telegraphy. In other words, while the sending key is held down for a dash, there will be a long series of oscillations in the antenna, and for the dot a short series. And these short and long trains of waves will spread out to the receiving aerial, where they will reproduce the same series of oscillations. But only a small part of the energy will act on the receiving aerial, because the waves, like those on the pond, spread in all directions and grow rapidly weaker. Hence the advantage of an extremely delicate instrument like the audion to amplify the signals received. The oscillations used in wireless telegraphy these days are very rapid, usually entirely too rapid to affect an ordinary telephone receiver, and if they did, they would produce a note of such high pitch that it could not be heard. So it is customary to interrupt the oscillations, breaking them up into short trains of waves, and these successive trains produce a note of low enough pitch to be heard in the telephone receiver. Of course, the interruptions are of such high frequency that in the sending of a dot and dash message, each dot is made up of a great many of the short trains of waves. Now, in radiotelephony, it is not necessary to break up the oscillations, but they are allowed to run continuously at very high speed and act as carriers for other waves produced by speaking into the transmitter. That is, a single speech wave would be made up of a large number of smaller waves. To make wireless telephony a success, it was necessary to find some way of making perfectly uniform carrier waves, and then of loading on them waves of speech. Of course, the latter are not sound waves, because they are not waves of air, but they are electromagnetic waves corresponding exactly to the sound waves of air, and at the receiving end they affect the telephone receiver in the same way that it is affected by the electric waves which are sent over telephone wires. The telephone engineers found that the audion could be used to regulate the carrier waves and also to superpose the speech waves upon them. And at the receiving station the audion was used to pick up these waves, no matter how feeble they might be, and amplify them so that they could be heard in a telephone receiver. Talking without wires. Attempts at long-distance talking without wires were made from Montauk Point on the tip of Long Island to Wilmington, Delaware, and they were successful. This was in 1915. The apparatus was still further improved, and then the experiment was tried of talking from the big Arlington station near Washington to Darien on the Isthmus of Panama. This was a distance of 2,100 miles, and speech was actually transmitted through space over that great distance. That having proved successful, the next attempt was to talk from Arlington to Mare Island and San Diego on the Pacific coast, a distance of over 2,500 miles. This proved a success too, and it was found possible even to talk as far as Honolulu. The engineers now felt confident that they could talk across the Atlantic to Europe, and so in October of 1915 arrangements were made to conduct experiments between Arlington and the Eiffel Tower in Paris. Although the war was at its height and the French were straining every effort to hold back the Germans at that time, and although there were constant demands for the use of radiotelegraphy, the French showed such an appreciation of science that they were willing to lend their aid to these experiments. The Eiffel Tower could be used only for short periods of time, and there was much interference from other high-powered stations. Nevertheless, the experiment proved perfectly successful, and conversation was carried on between our capital and that of France, a distance of 3,600 miles. At the same time, an operator in Honolulu, 4,500 miles away, heard the messages, and so the voice at Arlington carried virtually one-third of the way around the globe. After that achievement there was a lull in the wireless telephone experiments because of the war. But there soon came an opportunity to make very practical use of all the experimental work. As soon as there seemed to be a possibility that we might be drawn into the war, the Secretary of the Navy asked for the design of apparatus that would make it possible for ships to converse with one another and with shore stations. Of course, all vessels are equipped with wireless telegraph apparatus, but there is a decided advantage in having the captain of one ship talk directly with the captain of another ship, or take his orders from headquarters with an ordinary telephone receiver and transmitter. A special equipment was designed for battleships, and on test it was found that ships could easily converse with one another over a distance of 35 miles and to shore stations from a distance of 175 miles. The apparatus was so improved that 9 conversations could be carried on at the same time without any interference of one by the others. When it became certain that we should have to enter the war, there came a call for radio-telephone apparatus for submarine chasers, and work was started on small, compact outfits for these little vessels. Radio-telephones for airplanes. Then there was a demand for radio-telephone apparatus to be used on airplanes. This was a much more complicated matter and called for a great deal of study. The way in which problem after problem arose and was solved makes an exceedingly interesting narrative. It seemed almost absurd to think that a delicate radio-telegraph apparatus could be made to work in the terrific noise and jarring of an airplane. The first task was to make the apparatus noise-proof. A special sound-proof room was constructed in which a noise was produced exactly imitating that of the engine exhaust of an airplane engine. In this room various helmets were tried in order to see whether they could be proof against the noise, and finally a very suitable helmet was designed in which the telephone receiver and transmitter were installed. By summertime the work had proceeded so far that an airplane equipped with transmitting apparatus could send spoken messages to an operator on the ground from a distance of 2 miles. The antenna of the airplane consisted of a wire with a weight on the lower end, which hung down about 100 yards from the body of the machine. But a trailing antenna was a nuisance in airplane maneuvers, and it was also found that the helmet, which was so satisfactory in the laboratory, was not just the thing for actual service in an airplane. It had to fit very tightly around the ears and mouth, and as the airplane went to high altitudes, where the air pressure was much lower than at the ground level, painful pressures were produced in the ears which were most annoying. Aside from that, in actual warfare, airplanes have to operate at extreme heights, where the air is so rare that oxygen must be supplied to the aviators, and it was difficult to provide this supply of oxygen with the radio helmet tightly strapped to the head of the operator. But after considerable experiment, this difficulty was overcome, and also that of the varying pressures on the ears. Another great difficulty was to obtain a steady supply of power on the airplane to operate the transmitting apparatus. It has been the practice to supply current on airplanes for wireless telegraph apparatus by means of a small electric generator which is revolved by a little propeller. The propeller in turn is revolved by the rush of air as it is carried along by the plane. But the speed of the airplane varies considerably. At times it may be traveling at only 40 miles per hour, and at other times as high as 160 miles per hour, so that the little generator is subjected to great variations of speed and consequent variations of voltage. This made it impossible to produce the steady oscillations that are required in wireless telephony. After considerable experiment, a generator was produced with two windings, one of which operated through a vacuum tube, somewhat like an audion, and to resist the increase of voltage produced by the other winding. Then another trouble developed. The sparks produced by the magneto in the airplane motor set up electromagnetic waves which seriously affected the receiving instrument. There was no way of getting rid of the magneto, but the wires leading from it to the engine were encased in metal tubes which were grounded at frequent intervals, and in that way the trouble was overcome to a large extent. The magnetos themselves were also encased in such a way that electromagnetic waves would not be radiated from them. Instead of using trailing wires which were liable to become entangled in the propeller, the antenna was extended from the upper plane to the tail of the machine, and later it was found that by using two short trailing antennae, one from each tip of the wings, the very best results could be obtained. Still another development was to embed the antenna wires in the wings of the plane. It was considered necessary, if the apparatus was to be practicable, to be able to use it over a distance of 2,000 yards, but in experiments conducted in October, 1917, a couple of airplanes were able to talk to each other when 23 miles apart, and conversations were carried on with the ground from a distance of 45 miles. The conditions under which these distances were attained were unusual, and a distance of 3 miles was accepted as a standard for communication between airplanes. The apparatus weighed only 58 pounds, and it was connected with both the pilot and the observer so that they could carry on conversations with each other and could both hear the conversation with other airplanes or the ground. As a matter of fact, airplanes with standard apparatus were able to talk clearly to a distance of 5 miles, and even to a distance of 10 miles when conditions are favorable, and they can receive messages from the ground over almost any distance. A similar apparatus was constructed for submarine chasers with a standard range of conversation of over 5 miles. Apparatus was manufactured in large quantities in this country, and all our submarine chasers were equipped with it, as well as a great many of our airplanes and seaplanes, and we furnished radio apparatus sets to our allies which proved of immense value in the war. This was particularly so in the case of submarine detection, when it was possible for a seaplane or a balloon to report its findings at once to submarine chasers and destroyers, and to guide them in pursuit of submarines. The improved audion holds out a wonderful future for radio telephony. For receiving, at least, no elaborate aerial will be needed, and with a small loop of wire, an audion or two, and simple tuning apparatus, anyone can hear the radio gossip of the whole world. Telegraphing 1,200 words per minute. Some remarkable advances were made in telegraphy also. During the war and since, messages have been sent direct from Washington to all parts of the world. In the telegraph room, operators are connected by wire with the different radio stations along the coast, and they can control the radio transmitters, sending out their messages without any repeating at the radio stations. Long messages are copied off on a machine something like a typewriter, which, however, does not make type impressions, but cuts perforations in a long sheet of paper. The paper is then run through a transmitter at a high speed, and the message is sent out at a rate of as much as 1,200 words a minute. At the receiving station, the message is received photographically on a strip of paper. The receiving instrument has a fine quartz thread in it, which carries a tiny mirror. A beam of light is reflected from the mirror upon the strip of sensitized paper. The radio waves twist the quartz thread ever so slightly, which makes the beam of light play back and forth, but of course the motion is greatly magnified. In this way a perfect record is made of the message in dots and dashes, which are translated into the corresponding letters of the alphabet. Detecting radio spies. There is another radio invention which we contributed during the war that proved of utmost service in thwarting German spies, and which is going to prove equally valuable in time of peace. Although a war invention, its peacetime service will be to save lives. It is a very simple matter to rig up a wireless telegraph system that will send messages to a considerable distance, and simpler still to rig up a receiving set. European governments have always discouraged amateur radiotelegraphy, but in this country restrictions used to be so slight that almost any one could set up and use a radio set, both for receiving and for transmitting. When we entered the war, we were glad that amateurs had been encouraged to play with wireless, because we had hundreds of good radio operators ready to work the sets which the Army and the Navy needed. But this was a disadvantage, too. Many operators were either Germans or pro-Germans, and were only too willing to use their radio experience in the interest of our enemies. It was a simple matter to obtain the necessary apparatus, because there was plenty of it to be had everywhere. They could send orders to fellow workers and receive messages from them, or they could listen to dispatches sent out by the government and glean information of great military and naval importance. The apparatus could easily be concealed. A wire hung inside a chimney, a water pipe, even a brass bedstead could be used for the receiving aerial. It was highly important that these concealed stations be located, but how were they to be discovered? The wireless compass. This problem was solved very nicely. The Audion had made it possible to receive radio signals on a very small aerial. In place of the ordinary stationary aerial, a frame 5 feet square was set up so that it could be turned to any point of the compass. A few turns of copper-bronze wire were wound round it. This was called the wireless compass. It was set up on the roof of the radio station and concealed within a cupola. The shaft on which it was mounted extended down into the operating room and carried a wheel by which it could be turned. On the shaft was a circular band of aluminum engraved with the 360 degrees of the circle, and a couple of fixed pointers indicating true north and south. Now, when a signal was received by the aerial, if it struck the frame edgewise, the radio waves would reach one side before they would the other. Taking a single wave, as shown by the drawing, Figure 11, we see that while the crest of the wave is sweeping over one side of the frame, the trough of the wave is passing the other side. Two currents are set up in the radio compass, one in the wires at the near side of the compass and another in the wires at the far side of the compass. As these currents are of the same direction, they oppose each other and tend to kill each other off, but one of the currents is stronger than the other because the crest of the waves is sweeping over that side, while the trough of the wave is passing over the other. The length of the wave may be anything, but always one side will be stronger than the other, and a current equal in strength to the difference between the two currents goes down into the operating room and affects the receiver. Now, when the compass is set at right angles to the oncoming wave, both sides are affected simultaneously and with the same strength, so that they kill each other off completely, and no current goes down to the receiver. Thus, the strength of the signal received can be varied from a maximum when the compass is parallel to the oncoming waves to 0 when it is at right angles to them. To find out where a sending station is, the compass is turned until the loudest sound is heard in the receiver, and then the compass dial shows from what direction the signals are coming. At the same time, another line on the signals will be found by a second station with another compass. These directions are traced on a map, and where they meet, the sending station must be located. With this apparatus, it was possible to locate the direction of the station within a degree. After the station had been located as closely as possible in this way, a motor truck was sent out in which there was a concealed radio compass. The truck would patrol the region located by the fixed compasses, and with it the position of the concealed station could be determined with perfect accuracy. The building would be raided and its occupants jailed and the radio equipment confiscated. Even receiving sets were discovered with the portable compass, but to find them was a far more difficult task. For the receiving of messages from distant points without a conspicuous aerial, an audion would have to be used, and this would set up feeble oscillations which could be picked up under favorable conditions by the portable compass. Piloting ships to port. And now for the peacetime application of all this. If the compass could be used to find those who try to hide, why could it not also be used to find those who wish to be found? Every now and then a ship runs upon the rocks because it has lost its bearings in the fog. But there will be no excuse for such accidents now. A number of radio compass stations have been located around the entrance and approach to New York Harbor. Similar stations have been, or soon will be, established at other ports. As soon as a ship arrives within 50 or 100 miles of port, she is required to call for her bearings. The operator of the control station instructs the ship to send her call letters for 30 seconds, and at the same time notifies each compass station to get a bearing on the ship. This each does, reporting back to the control station. The bearings are plotted on a chart, and inside of 2 minutes from the time the ship gives her call letters, her bearing is flashed to her by radio from the control station. The chart on which the plotting is done is covered with a sheet of glass. Holes are pierced through the glass at the location of each compass station. On the chart, around each station, there is a dial marked off in the 360 degrees of the circle. A thread passes through the chart and the hole in the glass at each station. These threads are attached to weights under the chart. When a compass station reports a bearing, the thread of that station is pulled out and extended across the corresponding degree on the dial. The same is done as each station reports, and where the threads cross, the ship must be located. Not only can the direction finder be used to pilot a ship into a harbor, but it will also serve to prevent collisions at sea, because a ship equipped with a radio compass can tell whether another ship is coming directly toward her. And so, as one of the happy outcomes of the dreadful war, we have an apparatus that will rob sea fogs of their terrors to navigation. End of chapter 10.